Hello and welcome to discussion 11. Today we're going to talk about color and sensors. So first, for some announcements, exam 2 is next Thursday and the final project milestone is due the Tuesday after that. So that's the 27th. On to a little intro to colors. So in lecture we talked about how the human retina has 3 different classes of detectors: small, medium, and large cone cells, and they each have a different spectral response curve, and they each will have some final value. Here it's denoted S, M, and L, which will completely define the color that we will perceive. And in order to get these 3 values, we integrate over the spectral response curve of a specific cone cell multiplied by the spectral emission of whatever. So this is just the amount of light that is being emitted by anything we look at, really. And that'll give us our value for each of these 3 different cone cells. So in actuality, when we're calculating stuff like this, we can't do an integral, so we instead have samples. And because we have samples over these different distributions, then we can just express this as a vector dot product. And then of course we can also express it as a matrix multiplication. Okay, and then we also talked about displays. So displays, they have their own RGB values that they can emit. So typically when you look at displays, like very close up, they have 3 different types of pixels, or like little LED lights, that can each express one type of color. So normally this is split up into red color, green color, and blue color, and each of those pixels have their own spectral emission curve. This is like the same emission curve that you would see just out in the environment. They have their own specific spectral emission, and then if you want to determine the color that a person is going to see given some defined RGB value, then what you would do is you would multiply these 3 values with the spectral emission of your pixels, and then you would multiply that by the same thing back here. So this would just be the 3 spectral response curves, and that would again give us the color that we see when looking at a specific display. Okay, and then this last part is just talking about okay, say we're given some real world scene and we want to show this on a display. So we're given some real scene spectra, and then we have our response curves of our cones, and then we have our spectral emissions for a given display. How do we determine this RGB to show? Well, we just equate the 2 equations and then solve for RGB. Okay, on to question number 1. What is a metamer? Why are metamers useful? So a metamer, or metamers, are 2 different spectra that integrate to the same visual response. So conceptually, they are 2 equivalent high dimension signals which project to the same low dimension signal. And they allow us to reproduce real world scenes with hard to recreate spectra on screens. So just to put this in mathematical terms, if we look at this matrix formulation here, we have some S value that gets multiplied by these response curves, and we're given some S, M, and L value. Well, given the same response curve and given the same S, M, and L value, there will actually be multiple solutions to what S value you can plug in and get back this same response. And then just more intuitively, a metamer is two different spectra that look exactly the same to us. So when we're looking at a display and there's like a picture of a sun, it's not emitting the same exact values or same wavelengths that the sun actually does, but it does look similar to the sun because of metamers.